A generator, sometimes called an alternator, is a machine that converts mechanical power into electrical power. All generators are fundamentally based on the principle of electromagnetic induction. A motional EMF is created due to relative motion between two components, a stator and a rotor. The stator is a stationary part that typically supports a series of wound magnet wire coils. The rotor, or the rotating part, typically has a series of magnets attached to it. Generators can fall into one of two categories, axial flux or radial flux. For this demonstration, I've built an axial flux machine in which the magnetic flux acts in the direction parallel to the rotor's axis. It's typical to have a second rotor positioned on the opposite side of the stator. However, for simplicity, I chose to include only one. The principle of electromagnetic induction is conveniently summarized in Faraday's law of induction. The induced voltage in a coil of wire loops is equal to the time rate of change of flux linkage in the coil's cross-sectional surface. After making substitutions and applying assumptions, the equation can be simplified to the boxed formula shown. Here, N represents the number of wire turns per coil, B is the magnetic flux density external to the coil, and A is the coil's cross-sectional area. From the boxed formula, we see that the only time-varying parameter is the flux-linked area of the coil. Considering that dA dt is proportional to the speed with which the wire loop enters or exits the influence of the magnetic field, we can reason that the induced voltage in the coil is proportional to omega, or the rotor's angular velocity. This dependence on speed is often referred to as speed voltage. Thus, by varying the rotor's angular velocity, we can easily modify the electrical output of a generator. Another important consideration is magnet orientation and phase. The series of magnets, as you move around the rotor, must alternate in orientation, meaning north-south, north-south, and so on. This is due to the interaction between a single coil and multiple rotor magnets. In essence, if two magnets in sequence have the same field orientation, they will produce opposing voltages. Furthermore, since the voltage response is sinusoidal, there is an associated phase. Most professional grade generators are wired in 3 phases. Again, though, for the sake of simplicity, I've opted for a single phase arrangement where the coils are wound continuously in series from the same piece of wire, despite the fact that this is generally considered an inferior method. So in summary, I've listed in this table the 3 main parameters I attempted to optimize and some associated design decisions that I made. Okay, so this is my modest attempt at an axial flux generator. So here we've got the rotor, which rotates. It's got the magnets on it. Here's the stator block with the magnet wire coils. And then the wiring goes through the back, and I complete the circuit by attaching it to this multimeter here. Okay, so let's try it out. So obviously in its idle, it's inducing no voltage. So if I start at a moderate speed, you can see that the starts to go up. Higher speeds, the higher voltage. And then if I max it out, a little over 1 volt. While not particularly efficient, this machine suffices as a proof of concept, demonstrating how electromagnetic induction can be utilized in converting mechanical power into electrical power. We saw qualitatively that an increase in induced voltage corresponded with an increase in rotor angular velocity, thereby confirming the concept of speed voltage. This result is consistent with the predictions obtained via Faraday's law of induction. Thank you.